Okay, in this video we're going to look at some examples involving conservative vector fields. So in particular, we're going to be given a vector field. In each case, we're going to first prove that it is conservative. Then we're going to find the associated potential function phi. Then we're going to use that to evaluate the work done in moving an object under the influence of that force field or vector field from one point to another via a specified curve C. So in part 1 we have got this function. It's a 3D function, and this is the contour given. So we're going to start by proving that this is conservative. Now in our part 1 video we did show that proving that a force field is conservative is easily done by just showing that it is irrotational. So all we're going to do is to work out the curl of this force field and show that the curl is equal to 0. If the curl is equal to 0, then that tells us that the vector field is indeed conservative. So we have got 3x squared z here. Then for the j component, we probably going to run out of space here. So let's move this a bit lower. Curl of f, so partial x there, 2x plus 3x squared z, partial y, got z squared minus 2 here, and then partial z, we've got x cubed plus 2yz. So want to work out the determinant of this. The first component is going to be a partial derivative of this with respect to y. So it's going to give us 2z. Take away partial derivative of this with respect to z. So that's 2z as well. Then we're going to have partial derivative of this with respect to z. That is going to be 3x squared. So 3x squared here. Then partial derivative of this with respect to x again is going to be 3x squared. Then lastly, we're going to want to do partial derivative of this with respect to x, which is 0. Then partial derivative of this one with respect to y is 0 as well. So this is giving us 0 in the I component, 0 in the j component, 0 in the k component. So from this, this is telling us that f is indeed conservative. So part 1 or part A sorted. In part B, we want to find the potential function. So the potential function is the scalar function, which is such that f is equal to its gradient. So here we have got 2x plus 3x squared z. For the x component, we have got z squared minus 2 for the y component, and for the z component we've got x cubed plus 2yz. Now this is equal to the gradient of phi. So got phi x here, phi y, and phi z here. So the way we're going to find phi is by sort of solving this step by step or if I can use the term iteratively. So we're going to start with like the x component, find phi. So from the x component, for instance, the x component is telling us that partial phi, partial x is equal to 2x plus 3x squared z. Now from this, partial phi is equal to 2x plus 3x squared z partial x. Then we can integrate on both sides. So this is partial integration. So on the left hand side, this is going to give us phi. Recall, remember that phi is a function of x, y, and z. Then here we're going to integrate this with respect to x. So we consider everything else a constant. We just look at the only variable that's happening here is x, just like we do if we're differentiating partially. So the first term is going to integrate to x squared. The second one is going to integrate to x cubed z. Then instead of plus a constant, we're going to have a function when we're integrating partially. So here we've just integrated with respect to x. So the arbitrary function that we're going to have here could be a function of y and z, or it could be a function of y and or z. So we're going to say plus alpha, which is a function of y and z. So that is phi, but it is not fully determined. Then we're going to differentiate this with respect to y and compare with the equation we have there. So if we differentiate this thing with respect to y, there are no y terms here, so the only y term is that one. So it's going to be alpha y. According to what we have, this must be equal to z squared over 2. So we equate that. So z squared minus 2. So we require these two to be equal. Okay, so from here it tells us that phi y is actually equal to z squared minus 2. And so integrating partially again with respect to y now, it's going to give us z squared y minus 2y plus beta, a function of z this time, because remember alpha is a function of y and z. Then we can take this and plug it back into our equation for phi, which is this one here. So let's call this equation asterisk. Okay, so asterisk becomes, so phi is now going to be x squared plus x cubed z plus alpha, which is yz squared minus 2y plus beta, which is a function of z only. Then to find beta, we've got to differentiate this with respect to z and compare with the last component of our equation relating f and phi here. So this one here. So if we differentiate this thing now with respect to z, so we're going to get phi is z. So derivative of this with respect to z is going to give us x cubed plus 2yz plus beta prime this time. Okay, this must be equal to this one here. So so that must be equal to x cubed plus 2yz. Then this is telling us that actually beta prime is 0 because the other two terms balance out. If beta prime is 0, it tells us that beta must be a constant because beta is a function of one variable. So if we integrate that, we're just going to get a constant. So if we go back to this now and plug in beta, we finally have our phi. So phi, which is our potential function, is x squared plus x cubed z plus y z squared minus 2y plus a constant k. And so that sorts out our part B. Right. Then in part C, we want to evaluate the integral f dot dr along that contour. But we, from our part 1 video, we have seen that f dot dr simply going to be d phi from the beginning of the contour to the end of the contour. And so this is just going to be integral of d phi is just phi, which is what we have just found, minus 2y. The k actually we can keep, but we don't need the k because it's going to cancel out. Then at the beginning of our contour, here, when t is 1, x is going to be 0, y is going to be 2, and z is going to be cosine of pi on 4. Okay, then when t is 9, the x component is going to be 2, ln 9 over ln 3. The y component is going to be 54. It's going to be 9 times 2 times 3. The z component is going to be 9 over root 2. So that is what we're going to have. So when it comes to our integral here, so it means we're going to be integrating this from 0 to 1 over root 2 to 54, 9 over root 2. Then we just plug these in and work it out. We find that the work done here is going to be 2086 plus 36 square root 2. All right. Okay. So at this point, we're going to let you have a go at the second example here, which is this one. So you're going to prove that this is conservative, then find the corresponding potential function, then work out the work done in moving an object from -1 to 0 to 4 minus 3 5. Okay, so what you might want to do is to pause the video, have a go at this, and then when you continue the video, you can compare with our answer. All right, we're now going to scroll down to our solution for part 2. By the way, if you've got any questions on any of the stuff we're doing, please feel free to post in the comment section. Or if you'd like us to do a particular topic, just post it in the comments section. We hope these videos are useful. Please do not forget to subscribe to our channel to support and like the video. All right. Okay. So for part 2, for the first thing I want to do is work out the curl of f, which works out as shown there. The x component works out to this. The y component is identically 0, and that one works out to 0 as well. So that tells us that the force is conservative. So, and then for part 2, if we integrate the x component, we find this, where alpha is a function of y and z. We differentiate it partially, we find this, then we compare with the y component of the vector field. That tells us that derivative of alpha with respect to y is minus 4yz. We integrate that, we get this where beta is an arbitrary function of z. Plug it back into phi, differentiate now with respect to z, we get that, compare with what we have. So these two require them to be equal. That tells us that beta prime is 8z. We integrate that, and so this is going to be our final expression for phi. And then when it comes to the integral, it's simply going to be the value of phi at the the p2 endpoint minus the value of the function, the p1 starting point. And we get that the work done in this case is minus 50. All right, thank you for watching.